Welcome back to Brief Physics channel. In today's video, we shall take a closer look at how to calculate work done by a variable force. When we say variable force, we are referring to a force that is dependent on position or coordinates. It could be a force that is dependent on only one coordinate, say the x-coordinate, or a force function that is dependent on x and y coordinates. So the question is, assume that you have an object that is being acted upon by such a force. Let's look at the one-dimensional case first. And this object moves, say like that. How do we calculate the work done by such a force on this object as the object moves, let's say, from point A to point B along the x-axis? We note that the value of the force is different, say here, there, and so on, because it is a function of the x-coordinate. So the expression that we talked about in our previous video, namely work being a dot product of the force and the displacement, will not work, at least not in that form. The correct way to go about this is to systematically calculate the work done by that force on this object as the object moves, say, a distance dx from point A to that point, and then repeat the same calculation for the next interval dx, the next interval dx, and so on until you get to the final point. So let's determine the work done by this force on this object as the object moves a distance of dx. Let's call that work dw. We are using a language of calculus here. So the work done is fx, which is a vector pointing along the positive x direction, dotted into that displacement. In this case, the displacement is dx I hat, which is just fx dx. So that is the amount of work done for the first dx. So in order to get the total work done as the object moves from point A to point B, we sum up such a term that corresponds to many small intervals from point A to B. In this case, it is not a direct sum, but rather an integral, like that. The reason that it is not the usual sum, but an integral, is that such a small interval can be made infinitely small as we wish. And in such a limit, a sum will simply turn into an integral. It is just a result from basic calculus. Now let's come back to that integral formula that we have here. Now since the lower limit is a and the upper limit of x-coordinate is b, we have to write those limits in integral, like that. So there we have it. The total amount of work done by that force on this object as the object goes from A to B is given by that formula. Of course, this is just one-dimensional case. What about two-dimensional case? That means an object is moving in 2 dimensions under the influence of, let's say, a force which is dependent on both x and y coordinates. Of course, we take the x-axis to be that way and y-axis to be that way. So under the influence of this force, this object is moving from, say, point 1 to point 2 there. The coordinates of point 1 is x1, y1. The coordinates of point 2 is x2, y2. Note, this is point 1 and that is point 2. So generalizing the earlier equation that we have for work, the work simply becomes, again, the dot product of that force function with a displacement vector, call it dr, where dr is given by dx I hat plus dy j hat. Now it's a motion in 2 dimensions. So substituting dr with dx I hat plus dy j hat, and assuming that the force function fxy can be separated into x and y components like that, and substituting this in here, you see that work simply can be broken into two integrals. One is the x integral and the other one is the y integral, like that, with their own limits. So the limits for the x integral is x1 to x2, and for the y is y1 to y2. x1, x2, y1, y2. And that is it. Once you evaluate that two integrals, you will get the work done. The best way to understand all these results is by doing problems associated with these concepts. So let's look at problem 1. A force like that. This is a one-dimensional force. X is measured in meters. X in a particle changing the kinetic energy of the particle. Find the work done on the particle as it moves from coordinates x equals to 2 to x equals to 3. Does the speed of the particle increase or decrease? So let's calculate the work first. Work is given by such an equation which reduces into fx dx. So in this case, fx is 3x squared dx, and it goes from 2 to 3. X equals to 2 to x equals to 3. This is an easy integral to do. The answer is x cubed. And let's put in the limit, 2 and 3. So you get 3 to the power 3 minus 2 to the power 3, which will give you 19 joules. So if the work done, as you can see, is positive, what can you say about the change in the speed of the particle? Now we have to come back to the work kinetic energy theorem. Now since the work done is positive, namely 19 joules, that means the change in kinetic energy of the particle also is positive. That means the final kinetic energy minus the initial kinetic energy of the particle is positive. So that means the final kinetic energy of the particle is greater than the initial kinetic energy of the particle, which directly translates into the increase in the speed of the particle. After all, kinetic energy is given by half times the mass of the particle times speed squared. Problem 2. This is a two-dimensional case. This is a two-dimensional force with such an expression, x in meters again, acts on a particle, changing the kinetic energy of the particle. Find the work done on the particle as it moves from coordinates 2, 2 to 3, 0. Does the speed of the particle increase or decrease? Let's look at the force function. The x component of that force is minus 3x squared, that part. The y component of the force is a constant, which is 4, that part. So to calculate work, as we have seen before, it reduces into two integrals as follows, like that. So fx is minus 3x squared dx plus fy is 4 dy. Now let's look at the limits. The x coordinate is going from 2 to 3. The y coordinates is changing from 2 to 0. Now let's calculate the integrals. The first x integral will simply give you minus x cubed, and we have to put the limits like that. The second y integral will simply give you 4y, and then you have to put the limits like that. The first integral will give you minus 19, and the second integral will give you minus 8. So the answer for the work is minus 27 joules. So that is the work done. Now using the work energy theorem, we know work equals the final kinetic energy minus the initial kinetic energy. In this case, the work is negative. So that means the right hand side is also negative. So Kf minus Ki is negative, so that means Kf is less than Ki. The final kinetic energy is less than the initial kinetic energy, which directly indicates the speed of the particle decreases after the work is being done. And that solves the problem. Thank you for watching.